Hi all, hope you all are doing good. So today we are going to discuss about Newton's laws of motion. So Newton stated three laws. That is Newton's first law of motion, which is also called the law of inertia. The Newton's second law of motion, which states the net force is equal to mass times acceleration. And the Newton's third law of motion, which states for every action there is an equal and opposite reaction. But before trying to understand Newton's laws of motion, let us understand few basic concepts so that we understand these laws better. So Newton has formulated these laws around motion. So what actually is motion? So first we'll try to understand that. So motion is nothing but it is a change in position of the object over time. If an object is located in point A and it moves to point B after some time, then the change in position over that time is called motion. In case there is no change in position over time and the object continues to stay in the same place, then it will be called object is at rest. So in that scenario, the change in position will be zero, and then that state of motion the object is in will be called the object is at rest. So let us understand this motion better with an example. So now if you see here, I'm having a tree and I have parked my car near the tree. Okay, I have not started my car. So even after 40 seconds, I have not started my car. My car continues to stay parked here. So what will be my change in position? Even after 40 seconds, it is going to be 0. So now this state of motion will be called at rest. So we'll be telling the car or the object is at rest. Now what happens? I have started my car and my car starts moving. So I am on my way to my destination. So now my car is changing position over time. It was here, it came here after few seconds, after 1 minute it came here, after 2 minutes it came here. So my car is changing its position over time. So from here to till it keeps changing the position over time, that will be called the object is in motion. So my car is in motion. This state of motion will be present in the object. So this is what we understand as motion. Now what happens? Now after my journey has completed, I have completed my journey, I have reached my destination after 5 seconds, and now what this will be called? Now my car has come to a halt, so it is not changing any position right now, it is in the same spot, so it will be called again now object is at rest because there is no change in position over time now. So this will be called at rest. So hope you have understood what is motion. We will move on to the next concept and try to understand what is force. So what is force? Force is nothing but it is any push or pull on an object. So see, I'm having an object, and force is something if there is some push, or we are pulling the object, or we are pushing, that thing is called force. So what happens because of this push or pull, your object can move, its speed can change, your shape of the object can change, anything can happen to the object. So this push or pull on an object, which is felt by the object, is what is called your force. So now you're clear with the force. Now the next concept which comes is what is net force. Okay, now you understood what is force. Any push or pull on an object is considered as force. Now what is net force? So net force is nothing but it is sum of all the forces acting on the object. Okay, summation of all the forces acting on the object. So here what happens is while summing the forces which are going towards the right or going up are considered as positive forces, and the forces which are going towards your left and going downwards are considered negative forces. For example, in this object, we can see there are four forces acting on it. One is your gravitational force, which is always directed downwards, so that is a negative force. Next, we have this normal force, which is acting in upward direction on the object. So this is going upwards, and so it is your normal force. So how this normal force comes? This happens because there are electrons present on the ground as well as on the object. So when two surfaces or objects come in contact, what happens? The electrons are negatively charged, and for the object, the electrons are negatively charged, so they repel each other. So that repulsion is what produces this force called normal force. Now we have this force F1, which is an applied force. So somebody is applying external force on the object. These are naturally occurring forces, and this applied force is being applied on the object physically. And when we apply this object, we also get this frictional force. So when you're trying to push this object, you get the frictional force in the opposite direction, because we know the ground is not smooth, it's rugged. So it gives some resistance force while you try to push the object. So that is your frictional force. Frictional force, now this is going towards your left, so that is in negative direction. Okay, so now net force is what we will be adding up all those forces, and final force value which we get will be called your net force. So hope you have understood what net force means. Next is, we'll try to understand what is speed and velocity. Okay, speed simply tells us how fast an object is moving. Okay, the object can be moving very fast. So, speed tells you how fast something is moving. It tells you the magnitude. So, how much distance is covered in particular time. So, that is what is speed. For example, if I have a car, I can say my car is traveling at 20 kilometers per hour speed. That means the car has covered 20 kilometers in 1 hour. So that is what constitutes speed. But if you see here, the speed does not show me the direction in which the car is traveling. It can travel in the north, it can travel in the south, but that direction is not mentioned here when we talk about speed. So that is covered under velocity. So what is velocity? Velocity is the speed of an object in specific direction. So along with the magnitude, it also gives us the direction. So velocity simply tells you how fast something is moving and in which direction. So for example, if you see here, velocity, the car is traveling at 20 kilometers per hour speed towards north. So I am giving even the direction here when we mention velocity. So that is the difference between speed and velocity. Speed just gives you the magnitude at how fast the car or the object is moving, and velocity gives you what it gives you. So it gives you how fast the car is moving and in which direction. So that is velocity. Hope you have understood what is speed and what is velocity. Now we will see an important concept, inertia, on which the Newton's first law is based. What is inertia? See, inertia is nothing but it's the resistance to change. It is actually not a force, but it is the physical property which is possessed by any matter in this universe. So, what is matter? Matter can be solid, liquid, gas, plasma. All these are considered matter. So, inertia is the resistance to change, which is the physical property which is possessed by any matter. So, just the matter resists change. If you try to do something to this matter, the matter will resist the change. It will not give in easily. So, that resistance is what we call it as inertia. So, generally, the objects, no, they are considered they are lazy and they always resist change. So for example, we are having this object. This object is at rest. It is not moving anywhere. It is on the ground. So below we have the gravitational force and we have the normal force which we saw. So both are equal and opposite. So the net force is going to be zero when we sum both these forces. So now what do you think is holding this object in this same position of rest? Any guesses? Right. That is nothing but inertia. The object's resistance to change is what keeping the objects in the position it wishes to stay. So right now the object is at rest. So the object will continue to be at rest until unless I have some unbalanced force or net force pushing this object. The object will not move. It will stay stable like this. So it is because of this inertia the object continues to be at rest or in motion when there is no net force. And this inertia depends upon the mass. Mass, what is mass? Mass is the amount of matter which is present inside the object. The more the mass, the more the matter inside the object. Okay, so what is this? No matter, first of all. We know that it's solid, liquid, gas. So matter as mass and it occupies space. So mass is the amount of matter which is present inside the object. So the more the mass, the more the resistance to change. Okay. So the more the mass, the more the inertia. So mass is the direct quantitative measure of inertia. So we do not have any particular unit for measuring inertia. When we measure the mass, that what implies that is the inertia. So the unit of mass is kilograms and so the unit of inertia is also kilograms. So hope you understood. So inertia is nothing but we get inertia by measuring the mass. For example, we are having 10 kgs of mass, that means your inertia is also 10 kgs. That much resistance it will give. So as I told, the inertia is dependent on mass. So if you increase the mass, the inertia, which is nothing but the resistance to change by this object, will also increase. So more mass, more inertia. So 100, imagine, is it easy to move a 10 kg block or a 100 kg block? Which will be easier? 10 kg block will be easier because it has low inertia. How it has low inertia? Because it has less mass. So the inertia will be low, its resistance to change will be low, and so will be able to push this 10 kg box easily. Next comes the 100 kg box. This 100 kg box, it has more mass. So it will be very difficult to move this 100 kg box. Why? Because it has high inertia. It has high resistance to change. So the more the mass, the more the inertia. So mass is directly proportional to inertia. So if you see, imagine if there is no inertia. Okay, I don't have inertia. There is no concepts of inertia. The object does not have any resistance to change. What will happen? Imagine if there was no resistance to change, that is inertia. Even if I just touch the ball, it will no go at lightning speed. It will travel at lightning speed. It will travel at the rate of light. what will happen? How that is how fast the objects will start moving. Now, if there is no inertia, even if there is a big rock, just by touching the rock will move from its position because it does not have any resistance to change, so it will not continue to stay in that place. It's only because of this resistance to change why all these objects, your big uh, rocks or big objects, all are staying in position. It's only because of this resistance to change called inertia. So now you have understood what inertia is and the importance of inertia. So so if you see, this inertia is present when the object is at rest as well as when the object is in motion. So the inertia is present in all these cases. So now that we understood what inertia is, let us get into the Newton's first law of motion. Okay, so the Newton's first law of motion is called law of inertia because it is based on these resistance to change called inertia. That's why it's also called law of inertia. So what does the Newton's first law of motion state? The Newton's first law of motion states that an object at rest will stay at rest and an object in motion will stay in motion with the same speed and in the same direction unless acted upon by a net external force. That is, the objects at rest will continue to be at rest and objects in motion will continue to be in motion with a constant speed and in the same direction in a straight line unless it is acted upon by net force. So let us try to understand these laws better. So now we will see the example and try to understand these first law of motion. So what it states, the objects which are at rest will continue to be at rest. So if I'm having a ball, it is placed on the ground and it is not moving unless and until somebody comes and kicks the ball and applies some external force on this ball. The ball will continue to stay in this position. It will not change. So that's why they say objects at rest will continue to be at rest until acted upon by a net external force. Now, there is similarly the next situation which says if now we are kicking the ball and the ball is in motion. So, what the Newton's first law of motion says, the ball will continue to be in motion with uniform velocity, that is same speed and in the same direction, that is in a straight line unless and until it is acted upon by a net external force. So if there is no force acting on this object to change its direction or speed or anything, what will happen is the ball will continue to be in motion with the same velocity in a straight line. Okay, so now I just want to ask you people one question. What is that is okay, but in real life, have you seen the ball no continuously going in the same direction with the same speed? Have you observed that, any of you? You are kicking the football, but at some point the ball stops, right? Does it continue non-stop forever? That's what Newton's first law states. The ball will keep on moving with the same speed and in the same direction in a straight line forever until and unless there is any external force on it. But in real time, have you seen that scenario? You would have never seen that. The ball will always stop after some time. Why? Because on our earth we have friction is there, we have some forces like wind force which are acting on the football which will be stopping the ball. So even if you take an ice floor, you are pushing the ball on the ice floor, what will happen? The ball will be rotating on the ice floor continuously, but that also will come to a halt after some time. So this is contradicting with what Newton is telling. So how to achieve the Newton's ideal scenario where the object will continue to be in motion with the same uniform velocity in a straight line? That is possible only in out of space. You go to out of space, and there will not be any friction, there will not be any air pressure. So all these resistive forces are absent in the space. So there you kick the ball and the ball will keep moving continuously without stopping in a straight line with the same velocity forever and ever. It will never stop moving. So the Newton's first law is satisfied there. So hope you have understood. So on our earth it's difficult to achieve that ideal scenario, but in space you will be able to see that scenario work. Okay, so hope you have understood the Newton's first law of motion. Let us see one more example for Newton's first law of motion. We are having a box. This box is at rest. You know why the object is staying at rest? We have seen. Any guesses? Yes, it's because of inertia, the resistance to change. The object continues to be at rest. Now I'm having an object, and both of these people are pushing the box on either side in opposite directions with the equal force. So now, because the forces are balanced, they will cancel out. So when the object is acted upon by balance force also, it stays at rest. Only if there is some net force, here the net force becomes zero. So only if there is some net force, the box will move. Because the net force is zero, there is no force acting on the box. It will continue to stay at rest. Now this box is there. Now both of them are pushing from same direction. So what will happen? Now there is some net force acting on the box. So the box will move. So the box was at rest. Now it will start moving because now there is unbalanced force which is acting on the box. So we are having net force acting on the box. So now you have understood, until and unless there is no net force acting on the object will continue to be in its same state of motion, be it rest or in motion. It will continue to stay in that same state, the natural state. If it was at rest, it will continue to be at rest. If it was moving, it will continuously move with the same speed and direction in a straight line. So this gives you an idea of the Newton's first law of motion. Now that you have understood Newton's first law of motion, let us get into the Newton's second law of motion. So this is what your Newton's second law of motion is. So Newton's second law of motion states the net force is equal to mass times acceleration. So what is this, or what is being told in Newton's second law of motion? In first law, we studied that the inertia is what keeps the object in its state, and some net force has to be applied so that that object can be moved from its state of motion, whichever state of motion it is in. So that force which is required to break this inertia, overcome this inertia and push the object or accelerate the object, is what is your net force here, which Newton is mentioning. So net force here is equal to, how you will calculate that? You need to have the mass. How much mass is there? Mass is nothing but your inertia. That will state how much inertia the object has and how much acceleration you want to know or speed up the object, so that you can calculate the force required to break the inertia. So now we will see. the concepts. Here we'll try to understand what is mass and acceleration. And net force we have already seen, it is uh, the sum of all the forces. But in the Newton's second law of motion, how we are calculating the net force is we are multiplying mass with acceleration and finding the net force. So we'll try to understand what is mass and acceleration so that we can calculate the net force in Newton's second law of motion. So what is mass? Mass is nothing but, we had discussed earlier, it's the amount of matter which is present inside an object. The more the matter, the more the mass. The matter can be solid, it can be liquid, it can be gas, or it can be anything else. So if you are having 1 liter of water or you are having 2 liters of water, so you are having more matter. So that is what is mass. Now, what is acceleration? We have seen what speed is. Speed gives us the magnitude, distance traveled by time taken, how much distance is covered over a time. Velocity gives us, along with the distance traveled by time taken, also the direction in which the object is moving. Now, what is acceleration? Acceleration is nothing but how fast your velocity your velocity is changing over time. So this is nothing but your velocity over time. How the velocity is changing over time is what your acceleration is. Velocity includes both speed and direction. We know that an object is accelerating if it speeds up, if it's slowing down or changing direction. So because acceleration is change in velocity. So velocity is nothing but speed and direction. So if speed is changing or direction is changing, that is nothing but it is acceleration. That is, acceleration is nothing but, in simple terms, how we call is how fast your speed or your direction of the object is changing, how fast. The velocity gives us how fast the object is moving, in which direction, but acceleration will give you how fast your speed or direction is changing. So if I want to change my speed from 10 kilometers to 20 kilometers, so how fast I'm changing that? Am I fasting with changing the speed within 1 second, or I'm changing the speed over 20 seconds? So that is what gives you acceleration. How fast your speed or direction is changing is calculated using this acceleration. So acceleration is nothing but change in velocity by time. And so when your car is slowing down, what will happen? You're traveling with a certain velocity. When car is slowing down, that means you are changing the speed. So you're slowing down the car. So that means you are accelerating. So because it's in the opposite direction, that is, we call this as deceleration. Similarly, when the car is speeding up, when you are increasing the speed, what you are doing, your velocity is, you are going with a certain speed in certain direction, you are increasing the speed. So how fast you are increasing that speed is your acceleration. That time also we use the word acceleration, or acceleration is being done. Similarly, the car is changing direction, so it is now rotating in the circular part. So here again, change in velocity is acceleration. So here also we called the car is accelerating because it is changing directions. So if you see, you are traveling with certain velocity and your car is changing direction. See, it is because it's going in a circle, the acceleration is towards your center, pointing perpendicular to your velocity. So your car is turning like this based on your acceleration. So now hope you have understood what acceleration is and what mass is. Now we will try to know understand Newton's second law of motion. So what Newton's second law of motion states? It states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. In simple terms, it means that how fast an object speeds up depends entirely on how hard you push it and how heavy it is. Okay, just um, meet this, we will see it in detail what that means. So net force is equal to mass into acceleration. So based on the second law of motion, it states more force, more acceleration, more mass, less acceleration. So we will try to understand this statement given by Newton. So acceleration of an object is directly proportional to the net force acting on it. So this part first we'll try to understand. So acceleration is directly proportional to the net force acting on it. So for example, now we will see with an example how it is directly proportional to the net force. How it is proportional. So what is happening here? We are keeping the mass constant. For example, we are having two small balls of no same mass. Okay. Now, if I am pushing the ball with 5 Newton force, so I am pushing the ball slowly, what will happen? Your ball will move slowly forward. But the same ball, if I am pushing with 50 newtons, so big push, I'm pushing it fast, what will happen? Your acceleration will be high. It will move fast. No, it will accelerate fast. So this explains acceleration is of an object is directly proportional to the net force acting on it. So I am having a ball. If I push the ball slowly, what will happen? It will only move to small distance. If I push it fast, it will move to long distance. It will speed up fast. If I push slowly, it will speed up slow. So that is what explains the acceleration of an object is directly proportional to the net force acting on it. And that is more force, more acceleration. So this has been answered. Next part is acceleration is inversely proportional to its mass. Okay, so more mass, less acceleration. So let us take the example there. Now I am having two balls. One ball is 10 kgs and another ball is 100 kgs. And I'm using the same force for both the objects. So for 10 kg ball, I am pushing with the same force, 10 newtons force I am pushing. What will happen? Because the ball is having less mass, its acceleration will be high. Now, similarly, imagine 100 kg ball is there and I'm pushing with that same small force which I applied for 10 kg. What will happen? Will it move forward a lot? No, it will only speed up a little. It will not be able to push it much. So it will not speed so fast. It will be very slow. That's why they are telling the more the mass, the acceleration will be less. See, large mass, low acceleration, small mass, high acceleration. So these two concepts what explains your Newton's second law of motion. Now let us apply this second law of motion for our example. Okay, so Mm, let us expand the formula and try to study this. So Newton's second law of motion calculates exactly how much force you need to break the inertia. Net force is equal to mass into acceleration. Mass is nothing but the amount of inertia you have to overcome, which we saw. Acceleration is this is how drastically you want to change the object's velocity, how fast you want to change the object's velocity. And net force is this is the exact amount of effort to break that inertia and achieve that change. So this is your formula which is given by your Newton's second law of motion. Now we will apply it into a real life. Now what happens? Now I have my car which is 100 kilograms. The mass of the car is 100 kilograms. So my inertia is 1000 kilograms, sorry, 1000 kilograms of car, mass of the car. And I want to accelerate it to 2 meters per second square. So that much acceleration I want to achieve for my car. So I want to know how much force, with how much force I need to push this car so that I get this acceleration of 2 meters per second square. I want to calculate that and apply that force. So now we'll be applying the Newton's second law of motion, which states that formula mass into acceleration. So what I will get? I will get the net force as 2000 newtons. So this much amount of force is required for me to achieve the output of 2 meters per second square acceleration. To achieve this acceleration, I need to push my car with net force of 2000 newtons. Got it? So this is how we apply this Newton's second law of motion in our real time. So now finally comes your Newton's third law of motion. Okay, what is Newton's third law of motion? So Newton's third law of motion states that for every action there is an equal and opposite reaction. This means that when one object exerts a force on second object, the second object simultaneously exerts a force of equal magnitude and opposite direction on the first object. That is, now if we see here, a person is there and he is pushing against the wall. That is the action. So he is pushing against the wall with certain force. What is happening as per Newton's second law of motion? There will be a reaction from the wall. The wall will push you back with the same force you used to push against the wall. So that is your reaction of the wall. So this is what is happening. Like Newton explained, if there is one action, there is always an opposite reaction. Means you are doing an action, you are applying a force, the exact opposite with the same magnitude, a force is coming back on you. So how that is happening? Actually, this happens because both the objects are made of electrons. Okay, they have electrons in their shells. So these electrons in the atoms are what is repelling. So the repulsion between the both objects electrons is what causes this action and reaction. So you are repelled by the electrons of this wall, and the wall is the wall is repelling from the electrons of your body. So that's why you get this action and reaction. Let us see with another example. So here we have a table, we have a book, and now I'm placing the book on the table. So what force is acting? The book is exerting a force on the table, which is action, and in turn the table is exerting a force back on the book, which is reaction. Now these forces, you can see both are acting in opposite directions, so you might think they will cancel each other and there will not be any force. But you have to understand that here the forces are acting on different objects. So this force action is acting on the reaction is acting on the table, and this force action is acting on the table. So on the same object, if two forces are acting in different directions, that time we can call, no, they can cancel each other and become zero. But here they are acting on different objects. So that is one difference which you should note in Newton's third law of motion. That's why they have told from object A to B, B to A. So this is what that explains. Suppose object A exerts force A B on object B, and the latter exerts force BA on the former, then Newton's third law can be written as FAB is equal to minus BA, because both are in opposite directions. That's why minus sign. So hope you have understood the three laws of Newton. Okay. Now we will see the applications where these laws are applied in our real life in real time. Okay. So if you see the Newton's first law of motion, okay. So the Newton's first law of motion is applied in our seat belts which we use for our cars and by the astronauts who are floating in space for conducting experiments. So this is where the Newton's first law of motion is used. So how? If the seat belts, why they were designed? Because of Newton's first law. What it states, if the object is in motion, it continues to be in motion unless and until it is acted upon by an external force. So what happens when you are sitting in the car is in motion, along with your car, your body is also in motion. Okay, now you both are different objects, but you are sitting inside the car. Now the car comes to halt because of the sudden brake. What will happen? Your car has come to halt, your inertia has come back to rest, but your inertia is still in motion. So what will happen, because your inertia has not come to stop at the same time as that of cars, so you will be pushed forward. So if there was no seat belt, you will go and hit the windscreen of the car. That's why these seat belts have been designed for our safety based on the Newton's first law of motion. Now similarly, the astronauts know if you are going to float in space, you will be moving away with the constant velocity, no, without stopping non-stop in a straight line. So that's why to change direction or the speed, they have no jetpacks attached so that they can come back whenever they require to come back or change the direction using the jetpack, because you need an external force to change the direction as per Newton's first law of motion. So these are the applications for the Newton's first law of motion. Now we will see Newton's second law of motion. What are the applications? The Newton's second law of motion, we'll take a simple example. First of all, we'll take the shopping cart. So we have the shopping cart. When the mass is low, no objects are there, what will happen? It's very easy to, we require only less amount of force to push the cart. That's what we saw, right? More force, more acceleration, less force, less acceleration, more mass. So we saw the shopping cart is there. We have, if the mass is less, the acceleration will be more. If the mass is more, the acceleration will be less. Correct? So now initially when the shopping cart is empty, your mass is less, and so it will be very easy to push your cart. Okay, that will be very easy. But in case we start adding all the items or grocery items inside our cart, the mass increases. So what will happen? Your acceleration reduces. So you will be requiring more force to push this cart. So it will become slower when more and more mass increases. So this is one of the applications of the Newton's second law of motion. The other one is the Newton's second law of motion, the rocket launches. Okay, the rockets, what concept they're using? So rockets, as they move up into the space, what happens is the petrol is getting burnt. So what happens? The weight of the or the mass of the rocket keeps reducing. So we know as the mass reduces, the acceleration increases. So using that concept, the rockets, as they go up and up into the sky, their fuel reduces and the mass reduces, which in turn accelerates the rocket. So that is the concept they use for Newton's second law of motion in our real time. This is the applications. Next, finally, is Newton's third law of motion. The Newton's third law of motion, we know for every action there is an equal and opposite reaction. So we are having swimming. So in swimming, what happens? We are pushing the water backwards. So what happens? There is an opposite reaction, equal and opposite reaction. The water pushes you forward. So that's why you swim and you move forward while swimming. That is the application of Newton's third law of motion. The other one is your rocket propulsion, where your fuel burns and produces lot of gases. These gases are sent out of the rocket, which in turn pushes the rocket up. So gases are moved out in this direction and the rocket is moved up in the opposite direction. That's how the rockets are sent up into the sky. So hope you have understood Newton's three laws of motion. Uh, Hope you have enjoyed today's session. So if you like my videos, please like, share and subscribe. Thank you all.